Great. Let's get on with it then. Somehow, I don't know if anybody cares about this. Somehow when I was grading the quizzes, the last question from last time was the one with the area between these two curves. That was the most complicated one, but also the one that almost everybody got full credit on, and a few people just like messed up a little something. People screwed up the easier ones, but everybody did great on the harder one. Good job, everybody, except the few of you who lost a few points. Maybe I should have mentioned it for your sake. But yeah. All right, anyway, we were talking at the end last time about using the natural log or doing u substitutions which involve the natural log. I had just one more example we can throw out there. So another u substitution. The idea about when logs occur in u substitutions typically is when you choose the u to be the denominator of a fraction, and then you make the substitution and then use this rule, and you end up with a natural log in your answer. Although sometimes it goes a little bit differently. So here's just another example about the integral of natural log of x over x dx. I think I mentioned last time that when you have a fraction and you intend to do a u substitution, usually you choose the u to be to equal the denominator. That's typically how these things work. But that's actually not a hard and fast rule. And in fact, choosing the u to be the denominator in this case gets you nowhere. I don't know if you've ever noticed this. I'm going to write this in red. Don't write this down because this is going to be bogus. But I could just saying, well, I'll choose the denominator. So you could say, all right, what if I do u equals x, and then the du will be dx, like 1 dx, right? And then I could plug everything in. In terms of u's, this would say ln of x over u dx, but x is the same as u, and dx is the same as du, so this is actually ln of u over u du. And now I have completed the substitution. Everything is in terms of u's. Anyone have a comment about my substitution here? I feel like a nice big boy who has done the substitution. What do you say?
It's the same thing.
Yeah, this is actually the same thing as what I started with. I just changed the name of the variable from x to u. This actually does nothing. And in general, u equals x never works. Trust me, I've been there, kid. It just doesn't do anything to choose u equals x. So looking at this one, it is natural to think of choosing the denominator as the u, but in this example, it's a bad idea because u equals x never gets you anywhere. I suppose my only other option would be choose the top, at ln of x. There's really no other sensible thing to do in this case, I think. So from here, this is like my real answer. I'll just copy this down here. I'm going to do u equals ln of x, all right? It's weird to choose the top as my u, but what else are you going to do, right? Then what's the du in this case? That would be the derivative of ln x. It is 1 over x dx, of course. All right, that's the rule about the derivative of the natural log. And then we try, as always, I try to plug everything in. So the ln x becomes u. So this now says, just putting the u in, it says u divided by x dx. And as I usually do, maybe you can see where this is going, but as I like to, I'm going to kind of split apart this fraction. I like to take out the numerator separately like that. U times 1 over x and then dx. That can sometimes clarify things if you're not quite sure what to do. Any thoughts? What should I do from here to continue substituting? Yeah?
Replace 1 over x dx for du.
Yeah, 1 over x dx is du right here, this guy. So 1 over x dx becomes du. This is u du. And now I, again, feel like a good boy, but even better this time. Now, this is actually a successful substitution because now this is not the same as what I started with. It's quite a bit easier. I can do the integral of u is 1/2 u squared plus c. And then finally put the original variable back in. 1/2 ln x squared plus c. There you go. This is how we do it. So the moral of this example is like, sometimes you just gotta pick some weird thing to be the u. It's not always the denominator, it's not always the inside of parentheses or the inside of a square root sign, which is typically what we say. Those are good kind of slogans in general, but none of them is a hard and fast rule, all right? Excellent. Anybody, can we simplify? Can you go, isn't that the same as 1/2 2 ln x, and they can cancel that? Is that? No, actually, that's not allowed. What, can anyone say what's different about?
If x itself was squared, would you do that?
Yeah, right. So that is not correct. The rule about that is this. If you have the exponent on the outside, so this ln x, the whole thing to the exponent, you can't do anything with that. That's just no funny business. It is what it is, as our president would say about COVID. Right? Ln x to the r, that is not something you can simplify at all. Okay, great. That was just a leftover example from last time. One last thing to say about the natural log, and then today we're going to go on and talk about e to the x, because remember our sort of grand scheme in talking about these things is to define the logarithm first. The natural log is defined in terms of the area under the curve of 1 over x. And then from there you can define the exponential function as the inverse of the logarithm. But anyway, one last thing to say about ln, that this may be something that you have seen before in high school. We can use ln of x, or let me just say the natural logarithm. We can use the natural log to find derivatives more easily. I'll put more easily in quotes, because sometimes what we're about to do here sometimes does make derivatives easier to do, but sometimes it makes them more complicated. It's really just sort of a different way of approaching taking the derivative of any old function. The function you're taking the derivative of doesn't have to involve the natural logs at all. This is called logarithmic differentiation. Logarithmic differentiation. Logarithmic. Logarithmic differentiation. This is kind of a derivative trick, which is not all that difficult to do, but involves using the natural log and then taking derivative. For example, how about let's find the derivative dy dx for y equals this fairly complicated thing, x squared 7 plus x to the 10 over 5x squared minus 7x plus 4. All right. Now, the way that you would do this, like without this logarithmic differentiation trick, even if you don't know how to do that, you could just take the derivative directly here. This has nothing to do with logarithms by itself, and you would take the derivative there by using some kind of complicated combination of the quotient rule and the product rule and the chain rule, right? You would use the quotient rule because it's a fraction, but the top has a product in it, so you'd have to use the product rule as part of the quotient rule. And this product also has this thing which would require the chain rule. So it's a fairly complicated product rule inside of a quotient rule, and that product rule has a chain rule inside of it. Alternatively, you can do what we call the logarithmic differentiation trick. And the trick is, so here's the trick. Do ln on both sides before taking the derivative, and then simplify, and then take the derivative. This is the basic approach for the logarithmic differentiation. You take the natural log on both sides, and then use properties of the natural log to simplify what results. And then you take the derivative of everything. And you will see, if you do it in this way, actually the derivative step, you do some extra steps at the beginning, but in this particular example, the derivative step at the end actually does not require the quotient rule or the product rule or the chain rule, and maybe the chain rule, but you avoid the quotient rule, the product rule. That's the point of this this whole trick, and that's why it makes things more easily. All right, so let's just try it in this example, and then I have one for you all to try. This is not really hard to do once you see somebody do it. So the first step, do ln on both sides. All right, so it's ln y equals ln of the whole right-hand side, like so. 5x squared minus 7x plus 4. Okay. Then simplify. Now you can't do anything on the left side. I'm just going to leave ln y on the left side. But on the right-hand side, you can simplify that business using our rules. Our rules for simplifying the natural log. Can anybody suggest what can happen over here when you simplify? We had some rules about something or other. Yeah?
For the fraction, you can do the ln a minus ln b.
Yeah, right. So the rule is ln of a over b equals ln a minus ln b. So that turns this into the natural log of the numerator, that thing, minus the natural log of the denominator. All right. Can we simplify any further? Yeah?
Could you bring the 2 and the 10 out? Or just the, like that?
Yeah, these 2 and 10s are exponents. Yeah, I'm not this will happen eventually, but I'd like to do something else first. Yeah.
If you split it into ln x squared plus ln.
Yeah. This is the log of a product, and by another rule, so the other rule that I'm referring to, ln of a times b is ln a plus ln b, right? So do that, and then once you do that, it becomes clearer what to do with the exponents, but you do the exponents next. So this I will write as ln x squared plus ln 7 plus x to the 10, and then minus, can I split that other one out also into 3 pieces? The answer is no. You can do this, log can split up if it's a log of a product or a quotient, but not a log of a sum. If there are things added together on the inside, you just got to leave them like they are. So this other one cannot be simplified. Okay, and then one more simplification. Those exponents in the x squared and the other thing to the 10, those exponents can come out to the front of the log. So, and then this is my final answer in terms of simplifying. It's 2 ln x plus 10 ln 7 plus x minus, and then this other thing has to stay like it is. Right? Now, this may, I said the whole point of this trick is to do the derivatives more easily. You probably could have done it the old school way with the product rule and the quotient rule by now. But I will just point out that this is very much sort of formulaic. If you are used to doing this procedure, you can really jump from this all the way down to here. Because what I see here is, first of all, it's a fraction. That means this part will be subtracted, which I see here. The rest of it is a product, which means these 2 parts will be added together, which I see here, and these exponents will come down to the front. This is actually, these steps, I mean, it took me a while to explain it all, but it's actually very easy to do these steps. And if you know what you're doing, you can really jump all the way from here to here without much thought at all. All right? Okay, anyway, can we proceed? So all along this, of course, equals ln y. So in terms of my 3 steps up here, I said do ln on both sides, then simplify. We are now at the 3rd step. Take the derivative. Take the derivative on both sides. So on the left side, what we get is the ln y becomes 1 over y, and then the chain rule, dy dx. This is slightly weird. This is sometimes called implicit differentiation, which I hope you have seen this before, although even if you haven't, it doesn't really matter. When you take the derivative of something, ln of something, you get 1 over whatever that is, and then because of the chain rule, I have to multiply times the derivative of the inside. The derivative of y, of course, is dy dx. All right, and then I take the derivative over here also. And these derivatives are all fairly easy. 2 ln x becomes 2 times 1 over x plus 10 times ln 7 plus x becomes 1 over 7 plus x. Each time you're going to have to use the chain rule, so I should multiply this times additionally the derivative of the inside, which is the derivative of 7 plus x, which is 1. So actually it doesn't matter in this case. You could say times 1 if you like. And then minus, okay, this one, the chain rule does matter, but it's 1 over that stuff. and then times the derivative of the inside, which is 10x minus 7. All right. Again, this is a step which kind of looks like a lot when you write it down, but actually it's very easy to do. In particular, none of these steps involve the product rule or the quotient rule, which is that's what is preferable to this method. I will let you judge for yourself if it's really all worth it, but that's the purpose of this method. All right, and then my final answer, I'm almost there. You can now solve for dy dx. This involves multiplying y onto the other side. Now, I don't really want my answer to have a y in it because it's supposed to be the derivative of something or other, but the y is this, all right? So rather than writing a y in my answer, well, I'll write one step where there is a y. It'll say dy dx equals y times all of this stuff, right? I'll condense a little bit here. 10x minus 7 over 5x squared minus 7x plus 4, right? I multiplied the y onto the other side, and I kind of gathered together various fractions over there. And then for my final answer, which I want my answer to be in terms of x, because I'm supposed to be taking the derivative of a function in terms of x, this y I will simply replace by the original formula that I started with, which said y equals whatever, that big fraction, right? So this y is x squared, x plus 7, 7 plus x, I might as well write the same way around, to the 10 divided by that other thing, 5x squared minus 7x plus 4, times the rest of it, 2 over x plus 10 over 7 plus x minus 10x minus 7. You get the idea. And this is my final answer. All right. Wasn't that such a quick and easy trick? It's debatable whether, in this case, it would have been better to have done the product and the quotient rule to begin with. But what I'm saying is actually, if you're used to doing this procedure, actually all of the steps that I did are really quite easy. And other examples will go more or less the same way. Any questions about that? I got one for you all to try, if you don't mind. All right, let's try. Certainly, if you had done this example using the quotient rule, your answer would look very different from this. It would be simplified in a very different way, but it would be the same. How about try this one here? Find the derivative of y equals x to the 4 over 2x minus 1 times 3x squared minus 7x to the 5. See what you think. I'll walk around and see how you're doing. You should start by taking ln on both sides and then simplifying the right side as much as you can. Yeah, because you always do the derivative of ln. If it was just ln x, the answer is 1 over x. So for that reason, ln of this stuff is 1 over that stuff. But then if you have extra things on the inside, you can also do the chain rule, which means you also multiply times 2. So this is good. This log can split together 2 things multiplied. Yeah. Can we go here? Yeah, this is good. Alright.
This is like ln AB is like ln A plus ln B.
Yes.
But since it's on the denominator and you're already like subtracting this, would it be minus ln B?
Yeah, so one way to look at it is you could say the denominator like in parentheses is ln is plus ln.
Right, okay.
You also can. Okay. So it's good here.
It's like the whole thing has in parentheses, but like the negative.
So you could do this and then the denominator.
Yeah.
All right, people seem to be looking good on this one. I'll try and write down what I did. You take the ln on both sides first. And then when I'm going to split this up across the quotients and the products. If you think this through, if you work it out, you will find that really anything which appears on the top ends up having a plus sign in front of it, and anything which was in the denominator ends up having a minus sign in front of it. So it's going to end up like this, and then minus ln of this other business, 3x squared minus 7x to the 5, right? You could have done this in 2 steps if you like, by first doing the quotient x to the 4 and then minus ln of the entire denominator, but then that entire denominator splits apart into 2 things. Be sure to distribute a minus sign. They should both be negative if you did that step properly. All right, and then these exponents can come out front, and then that'll be basically it for my simplifications. This one, the exponent of 5, comes down. Right, that's ln y. And then we can take the derivative on both sides, and this involves a bunch of simple chain rules. So doing the derivative on both sides. On the left, I get 1 over y dy dx. And on the right, I get here 4 times 1 over x minus, this is going to be 2 over 2x minus 1. If you like, you can remember this formula about derivative of ln with some stuff inside. The answer is g prime of x over g of x. This is probably if you can remember that way of writing it, the easiest way to write these answers. Each time what's inside the natural log ends up in a denominator, and the derivative of that stuff on the inside ends up as a numerator. And then I got minus 5 times 6x minus 7 over 3x squared minus 7x. All right, I think I did that right. And then finally, you multiply y to the other side and replace the original x values or x variable with the y's. So it looks like dy dx equals y, which is going to be the original thing again. So that's x to the 4 over this business. And then times the stuff that we had from before. 4 over x minus 2 over 2x minus 1 minus 5 times this stuff. There you go. This is the derivative. This is the logarithmic differentiation procedure. Sometimes useful, although the product rule and the quotient rule is always a valid alternative. Right? Yes?
Can you multiply the 5 by the numerator?
Sure, yeah. You'd have to distribute 60x. Well, yeah, plus 60x. No, minus 60x plus 35, something like that.
Minus 60?
30x.
30x?
Yeah, 30x. Sorry. I said it wrong too many times. Yeah. All right, great. Let's get on with it then. So those are all the things that I want to say about the natural logarithm. All right. All of this, remember, being done without ever referencing exponents at all. So what I would like to talk about for the next little bit is, what does this have to do with exponents? So this is the relationship between ln x, and of course everybody knows it is intimately related with e to the x. But we should try to kind of unpack that. In particular, the way that most people learn this material is, first you learn about e to the x, and then they say ln of x is defined to be the inverse of e to the x. All right? We are going to do this the other way around, though. So we already have a definition for e to the x, and so we'll discuss the inverse of e to the x. Sorry, I said it wrong. The inverse of ln x, right? ln x is already defined. We haven't really talked at all about e to the x, but we should be able to define the e to the x as being the inverse of the ln of x. That's the idea. So I will remind us from last time we talked about this, the graph of ln x is, sorry, I should put the axis in the middle there. The graph of ln x looks like, here is 1, and it goes like so, right? Maybe I'll move this down a little bit. And there was a special value over here called e, and e, the definition of the number e is it's the number which goes up to 1 there when you do ln of x. So this is the graph of ln x, all right? And in order to define the exponential function, we define it as being the inverse of this graph. So the inverse you can do just straight up on the graph by sort of reflecting across this line here, right? This, of course, is the y equals x line. And the inverse gives you another function. Now, the inverse, I'm trying to do the mirror image of this across this line. It ends up looking like that, basically, right? Although I'm going to try and be a little bit more careful. Actually, this line, it should go through 1 because this one goes through 1 over here, right? So when you flip it over, it should go through 1 right here. This line, it approaches this y-axis asymptotically as it goes down. What that means is the inverse, when I flip it over, should approach the x-axis asymptotically like this. So let me do this a little more carefully. It should approach the x-axis like an asymptote like that. Right? It should go through 1, and then it should continue going up that way. All right? And this graph is a graph of the inverse of ln x. Now, anybody paying attention will notice that doesn't that look kind of like the graph of e to the x? Yes, it does. The inverse of ln of x. And just sort of temporarily, I'm going to give that inverse function a name. So let's define, I'm going to call it exp of x to be the inverse of ln x. Exp of x. This is sometimes the notation that people use for the exponential function for e to the x. It's sometimes written that way, like in programming languages, it's often written as exp, like that. And it is defined to be the inverse of the natural log of x. And what we are going to be talking about for the rest of today, and maybe a little bit on Friday, is, first of all, can we think of, or can we demonstrate the basic properties that everybody knows about the exponential function? in particular that the derivative of e to the x is e to the x. That's kind of the most important property from a calculus point of view. And also, can we, maybe a more pressing preliminary question is that actually an exponent? Well, is that actually an exponential function? Like, just the way that I said this, I just said this is supposed to be the inverse of that. That doesn't necessarily mean that this graph represents some number e to the power x, right? I mean, it's not, there's no reason to think that this would be some power of some number. So this is the very immediate basic question: is that actually an exponential function? But it turns out we can work this out. So remember, I will have you note, we have this property about the natural log, right? Or ln of x. And if I use, if I plug in here x to be the number e, so plug in x equals e, and now it says ln e to the r equals r ln e. And what is ln e? This is the definition of the number e. Ln e equals 1, all right? And so what I have here is ln e to the r equals r. And then what this means, I have to think in terms of inverses, right? The natural log of this equals that. I can write this the other way around in terms of the inverse function of the natural log. So in terms of exp, can anyone say what would that say if you wrote it the other way around? What I'm trying to do is something like, if you know something like f of a equals b, you can also say this is like interchangeable with a equals f inverse of b, right? And that's kind of what I want to do here. Here I have the log, which is a function. Exp is supposed to be the inverse of that. Can anyone write this the other way around using the inverse instead of the ln? It's clear what I'm asking here. Yeah?
Would it be e to the r ln x? Or no, would it be e to the r 1 over x times r? I'm trying to think what we should do.
Instead of like to get the inverse here?
Yeah.
Yeah, remember this inverse doesn't mean 1 over, it just means the inverse of the function. So right here, I would say the inverse of ln, but that's what I've been calling this exp function. Define exp of x to be the inverse of ln. So over here, you want to see exp of r, I think is what you're going to say. Yeah, great. So this is writing this equation again, just the other way around. Instead of this function, I'm using its inverse, and you put it on the other side. All right? This is a little weird, I know. But what this demonstrates here, so e to the r equals exp of r. Generally speaking, I don't really like calling it r, so in generally, if I use x for the variable, exp of x equals e to the power x. And this means that this inverse of the logarithm, it actually really is equal to a power of the special number e, all right? This is, this, in my opinion, is kind of a remarkable or interesting fact, all right? So what this means is, so the inverse of ln x actually equals powers of the number e. All right? There was no obvious reason why that should be true, but it turns out, turns out to be true because of all that stuff that I just said. All right? The inverse of the natural log actually equals powers of this number e. All right? So the inverse of the natural log is this function e to the x. And now I'm not going to write exp anymore because we have a better way of writing that function. So ln x and e to the x are inverses. All right. And this is really the main purpose of the natural log, is that it functions as an inverse to e to the x. And so you can use this in you can use this for solving kind of algebraic equations. So that means, in one way of saying this is any equation using ln x can be rewritten in what they call the exponential form. So what I mean is something like, if you say ln of 2x plus 7 equals 5, this would be an equation written in the logarithmic form, but I can write the same thing again using the exponential form by just writing everything the other way around, using the fact that the inverse of the ln is equal to the exponential e to the x. Can anybody say, how would you write this using e's instead of logs? You would kind of write it the other way, yeah?
It would be e to the 5 equals 2x plus 7.
Yeah, excellent. Because the inverse of this ln is basically this e. And so if you are going to write it the other way around, what that means is, instead of putting the log on this side, you put the e on the other side. This is how a function interacts with its inverse. All right? E to the 5 equals 2x plus 7. Great. What's so great about this, actually this is super useful in real life. I mean, in particular, it means I can solve this here for x, right? If you subtract the 7, I will just say x. Well, we can now solve for x, right? You subtract the 7 and divide by 2. Where this original formula, there's no way to solve for x here. At least not without doing some kind of step like what I just did. All right, so this is, in a sense, what's useful about this fact that e's and the natural logs are inverses of one another. All right, and you can also solve for x when it's inside of an exponent. So we can do something like, here's two kind of similar examples. Solve for x. If I begin with x inside of a log, then the way to solve for x here is by first rewriting this in its exponential form, which means you take the log away from one side and put the e on the other side. So in this case, it would say e to the 12 equals 10x plus 1. And then this can be solved through x, right? E to the 12 minus 1 equals 10x. X is 1/10 e to the 12 minus 1. All right? I solve this by switching the log to an e. And you don't exactly switch this to an e. You have to put it on in the correct spot, right? There's a very stupid math joke involving the phrase "with ease." I can solve this with ease. You get it? I don't even have to tell you the whole joke. It's beneath my dignity to tell you the whole joke. But yeah, I solve for x with ease. Anyway. Or you can also solve for x when the x appears inside of an exponent. So for example, if I have something like e to the x minus 2 equals 7, I can solve this for x by putting it back into the logarithmic form. Can anybody say, what would it look like if I write this using ln instead of the e? Yeah?
Would be x minus 2 equals ln 7.
Yeah, I like that. You sort of take the e away from one side and insert the ln on the other side. This is how inverse functions work. And then, of course, you can solve this for x, right? 2 plus ln 7. Assuming you have like a calculator with the ln button on it, you can solve that. You have solved for x. All right? Excellent. Great. Just to emphasize here, since they are inverses, we have a few more minutes left. E to the x and ln x are inverses. This means automatically that when you plug one inside of the other, they kind of cancel. So what that would look like is ln of e to the x. Because those are inverses, the ln kind of cancels the e, and what you end up with is just x. All right? They cancel. Now, sometimes I know none of you would do such a silly thing, but sometimes I see people like, oh yeah, they cancel. So it's like this, I cross those out, and then my answer is like a tiny little X up there, because they canceled. There's no such thing as like a tiny little X up there. When I say they cancel, I just mean the log and the E kind of kill each other, and all you're left with is X, not to the X. Don't I just get to the X? No, there's no such thing as to the X all by itself. It's X, all right? And also the other way around. So it is also true, if you put the E on the outside, E of ln x like that also is equal to X, right? This is what it means when you say they are inverses of one another. And then let's talk about basic rules of exponents. Now this, you could say, is a basic rule of any exponents. But we can actually prove these using the log, which I don't want to get into the details of it, but rules for exponents. They are things I'm referring to, something like e to the a plus b equals, anyone remember this rule? E to the a times e to the b. And you have to just, this can be a little confusing to keep it straight. With a log, if you have multiplication on the inside, it turns into addition on the outside. With an exponent, it's the other way around. Addition inside of the exponent turns into multiplication of the two exponential functions. And then, of course, there's also e to the a minus b. This is equal to e to the a divided by e to the b. And then another important one is something like this. E to the x to the power r. Anyone remember how to handle that? Yeah?
You're just multiplying them?
Yeah, you just multiply. So this becomes e to the rx, all right? Each one of these are all sort of inverses of the ln rules, right? You can, I think, see the relationship. The last one there is a version of this rule, right? ln of x to the r equals r ln x, right? Here you have, sorry, this is hard to read, x to the power r. In both cases, you have somehow like an exponent turning into a multiplication, right? Here, this exponent turns into a product here, and here this kind of exponent inside of an exponent turns into a product. They are kind of the same rule written in the other way around. I don't think we need to go through the details of all of them, but maybe we could let's just talk about the first one specifically. How would we get the first one there? If I start with, so to show e to the a plus b equals e to the a e to the b. This is a formula written using e on the left. I can write it instead using ln. So use ln instead. This transforms into, I'll put it down here. Instead of the e on the left, I'm going to just write a plus b. And on the right side, it now says ln e to the a, e to the b, right? This is weird, but I wrote that original formula, which was using an e on the left. I'm writing it instead using the natural log. And why would you write it this way? It's because actually this formula that I just wrote, it is clear why is that true. So this is true since you can just start with the thing on the right, ln e to the a, e to the b, and this can be simplified. What can I do to simplify that? Yeah?
ln of b to the a plus ln of b to the b.
This is the rule about natural log of a product becomes the sum. And then what happens with those? ln kills e, and you just, it's a and b, not b and b. Thanks. And then the ln's cancel the e's, and I get a plus b, which is what we wanted, right? This equals a plus b. So that's the same as this, which is the original rule. All right, so all of these rules about powers of e are actually sort of just a rearranged version of the rules about the natural log, which we have already discussed. All right. We got 4 minutes remaining. I think that's enough time to say one last thing. The most important property about e to the x, when you're, when your friends at lunch ask you, what's so great about e to the x? Probably, to me, if someone asked me this question in the club, I say the derivative of e to the x is e to the x. To me, that's the important property of e to the x. It hasn't come up for me in the club. But that's because I don't go to the club. I imagine, as many people, if you like me, never go to the club, maybe you wonder sometimes, what is the club really like? Every idea I have about the club makes me want to stay away from the club. But I like to imagine that people are going to walk up to me and ask me calculus questions. It's the only way I can be successful in the club. How about derivative of e to the x, all right? From what we've already done, this is actually going to be pretty straightforward. So we start with this, y equals e to the x, and the question, of course, is what is dy dx? Well, we can use our old friend, the logarithmic differentiation. So what that looks like, remember the strategy is take the log on both sides and then simplify. All right, so we go ln y equals ln e to the x. So I'm doing this log differentiation. Log diff. You take the ln on both sides, then simplify on the right side. What can you get when you simplify on the right side? X. Yeah, ln e to the x just straight up gives you x. So this says ln y equals x. And now we take the derivative on both sides. On the left, as always, we get 1 over y dy dx. And on the right, what do you say? 1. Yeah, derivative of x equals 1. And so solving for dy dx, we get dy dx equals y, and plugging back in from the beginning, dy dx equals e to the x. There you go. You are now the hero of the club. This is why the derivative of e to the x equals e to the x. All right? And I think maybe I will leave it at that for today.